Bismillahirrahmanirrahim. Students, in these lectures, we discuss the numerical problems of three-phase systems. As we discussed all the theory earlier, but I think that we must discuss phase rotation also. That is phase sequence. Yesterday, when I took the live session, I feel that most of the people asked about what is phase sequence. So it is necessary to discuss phase sequence first and then shift towards numericals. So let's start from phase rotation or phase sequence. Let's take the three-phase alternator design. What is alternator? Alternator is a generator, AC generator, which alternates, which supplies AC against the rotations, against the mechanical input. That's why phase sequence. So the direction of rotor, we have two options. Either we rotate the rotor in counterclockwise direction or in clockwise direction. So against the direction of rotation of the rotor, which rotates in a certain magnetic field, it produces a voltage. So it produces a particular phase sequence. Phase sequence is a voltage, particular voltage which attain its peaks at a particular time. The phase angle shift of 120 is a function of actual rotational angle shift of the three pairs of windings actually. In this figure, you see three pairs of windings, and the windings are 120-degree apart from each other. And we split these windings into different pairs. That is 1A, 1B, same winding, then 2A, 2B, and 3A, 3C. Means same coil, its position changes, right? It is reference value and it changes the value. If the magnet is rotating clockwise, winding 3 will generate its peak instantaneous voltage exactly 120 degree of alternator shaft rotation after winding 2, which will hit its peak 120 after winding 1. See this figure, it shows to you, see this figure, winding 1 is peak and winding 2 its peak. Its peak appears exactly after 120 degree. The magnet passes by each pole pair at different positions in the rotational movement of the shaft. So the rotational movement changes every time and the angle degrees changes every time. Where we decide to place the windings will dictate the amount of phase shift between the windings, AC voltage waveforms. If we make winding 1 hour reference voltage source for phase angle 0 degree, then winding 2 will have a phase angle of minus 120 or 120 degree lagging or 240 leading. See the phase 3, its peak comes, if we take our phase 1 as a reference, then the winding 3 its peak comes after 240 degree. Means phase 3 lags phase 1 by 240 and phase 3 lags phase 2 by 120 and so on. Phase 1 as a reference, then phase 2 and then phase 3. So let's let's rub these arrowheads. This sequence of phase shifts has a definite order. For clockwise rotation of the shaft, the order is A, B, C or 1, 2, 3. See, the order is A, B, C or 1, 2, 3. Winding 1 peaks first, then winding 2, then winding 3. See, winding 1, winding 2, and then winding 3. So this order keeps repeating itself as long as we continue to rotate the alternator's shaft in a certain direction, that is counterclockwise direction. However, if we reverse the rotation of the alternator shaft, that is in clockwise direction, the magnet will pass by the pole pairs in the opposite sequence. Instead of 1, 2, 3, we will have 3, 2, 1. 3, 2, 1. So now winding 2's waveform will be leading 120 ahead of 1. See, winding 2 leading ahead of 3 to 120, and 3 will another 120 ahead of 2. Now the sequence is 3, 2, 1. This was supposed to be ABC, this one is ACB. The phase sequence changes just by the changing the rotation. Alternate when alternator rotates in opposite direction, the phase sequence changes. The order of voltage waveform sequence in a polyphase system is called phase rotation or phase sequence. If we are using a polyphase voltage source to a power resistive loads, phase rotation will make no difference at all. Whatever 1 to 3 or 3 to 1, the voltage and current magnitudes will be the same. There are some applications of three phase power as well we see shortly that depend on having phase rotation being one way or that other. Since voltmeters and ammeters would be useless in telling us that the phase sequence of an operating power system is what. So phase sequence, as I have told earlier also, that phase sequence is important for the three phase motor supply also, because if a motor is have a supply of phase sequence, let's say ABC, the direction of motor is certain, for example clockwise, and when you change the phase sequence of a three phase supply motor, for example ACB, the rotation of the direction of motor changes. That is, if before it was in clockwise direction, now against the change of phase sequence, it rotates in the opposite direction. So this is the importance of phase sequence. Let's move to the next slide. Before talk about the three phase, we start our analysis from single phase power systems. The most important of three phase circuits is well recognized by those who deal with electricity and its use. Three phase electrical sources are the most effective means of transmitting electrical current over long distances, and three phase motors offer many advantages over single phase motors. While the electrical service delivered to residents in United States is commonly single phase, larger users typically are served with a three phase electrical services. So in general, three phase loads are considered either balanced or unbalanced. A three-phase circuit is considered balanced if the voltages, currents, and power factors in all three phases are identical, that is same. Conversely, when any of these parameters are not identical, the circuit is classified as unbalanced. That means the impedance being not same, the current, the voltage not being the same. The computations of electrical properties of balanced loads are relatively straightforward and may be performed by simple computations. On the other hand, the calculations of electrical properties of unbalanced three-phase circuits become somewhat more complicated. To determine the currents in unbalanced circuits, a greater understanding of the subject is required. For a variety of reasons, it is often becomes necessary to calculate the currents in both balanced and unbalanced three-phase circuits. For example, the magnitude of the current may be needed to properly size conductors, conduits, relays, fuses, circuit breakers, transformers, and etc. Furthermore, the calculations of currents are often needed to demonstrate that an installation will be in accordance with the applicable codes such as National Electrical Code. Usually of large amounts of the electrical power, as commercial buildings or industrial installations are generally supplied with a three-phase electrical supply. The three-phase services could be either the three-wire or a four-wire type. Within commercial and industrial installation, circuits would typically be divided into both single-phase and three-phase circuits. The three-phase circuits would be used to power motors, whereas the single-phase branches of the three-phase services would typically be used for lighting, heating, and fractional horsepower motors. A common electrical services to commercial and industrial users would be normally 480, 360, or 50 hertz, depends upon the area. For example, US and United States, The supply frequency is 60 hertz, and the supply volts is 120 single phase. And in European standards, supply voltages are 440 and 50 hertz. So it depends. The design is changed actually. So before moving on to three-phase circuits, it is helpful to first review and understand the principles and terminology applicable to single-phase circuits. So single-phase circuits, if the load resistor power dissipation were substantial, we might call this a power circuit or power station. You may consider this as a source, and this one is a load. This is a power station. This one is a user. So power station supplies and user uses. So in this case, supply voltage is 120 and each load is of 10 kilowatt. So supply is connected and the load is connected to parallel to the supply actually. So from a basic knowledge, we know that power is a product of voltage into current. And if you want to find the current is nothing but power over voltage. So power in this case, that is load power, is 10 kilowatt each. So current is nothing but power over voltage. So when you divide it, the power to the voltage, you got 83.33 amperes for each load resistor. That is, each load consumes 83.33 amperes, and that load current goes to each branch. And what is the total load current? You just apply Kirchhoff current law at particular node, you find the current, that is sum of these two load currents. So total current being 166.67 amperes, and total power being utilized is the sum of the total power of the load, that is 10 kilowatt plus 10 kilowatt. So total power utilized is 20 kilowatt in this case. So in this case, and because amperes are large in magnitude, so the wire gauge required is of larger diameter, having more weight and having more cost. So the alternate way is to supply the same load with a change in the voltage, that is the voltage being 240. That is before it was 120, now the voltage supply changes to 240 volts. This is again single phase system. It supplies the same load, that is 10 kilowatt. And in this case, if you see the current being half of that what you find earlier, the current is 41.67, which is half of the earlier current. So current being halved and the total current being the also being halved, right? So for this system, you may say this, yes, your copper conductor dia is lesser because it handles less current. So weight is less, so the cost on the conductor being less. So this one is economical. Yes, you can say this one is economical. This is a good way to supply. That's why we increase the voltage of supply. So another case, you can connect the load in the series, but in this case, there is the currents pass are different. That is 83.3 amperes that are coming towards the source, and 83.3 towards C. The outgoing current, incoming current are same, but the directions are opposite. So this in this system, the trade-off between efficiency and danger is that one which European power system designers have decided to risk all their households and appliances operating at nominal voltage of 240 volts instead of 120 volts as it is in North America. That is why the tourists from America visiting Europe must carry small step down transformers for their portable appliances to step the 240 volts AC volts power down to more suitable to 120 volts AC. So this being actually the US standards has 110 volts 60 hertz supply or 120 volts 60 hertz, and European standard is 240 volts 240 volts 220 volts or 50 hertz supply. It is for the point of view of danger and risk safety point of views. So this system is called split phase power system. Three small wires are still cheaper than two wires, indeed with the simple parallel design. So we are still ahead on efficiency. So it's another way to supply the load is to take the center tape step down transformer with center tape. If you see the taps is center, and it gives the taps are taken between the center, that is it is the supply of 240 volts, and you take the center tape, it will split into 120 and 120. So this is another way to supply single phase or power the single phase loads. And this one is a representation of polar form, and this one is a representation of rectangular form. In rectangular form we have a real part and an imaginary part. In polar form we have a magnitude and the phase angle. Just note down the second phase is just 180-degree apart because the polarities. The first phase is like polarity positive negative, and the second have a polarity like negative positive. So it is 180. The phase angle being 180-degree because the polarities are, or you can monitor from here. See the polarity of this source and the polarity of this source. So polarities are opposite, so they are you can say 180-degree apart. So conclude this section. Single phase power systems are defined by having an AC source with only one voltage waveform. A split phase power system is one with multiple in phase AC voltages sources connected in series, delivering power to loads at more than one voltage, which with more than two wires. They are used primarily to achieve balance between system efficiency, low conductor currents, and safety, that is low voltages. Split phase AC sources can be easily created by center tapped the coil windings of the transformer or alternators as shown in this figure. So we conclude that single phase supplies are used for to fed single phase loads, small loads. Now we move towards the three phase system. Bismillahirrahmanirrahim. Now let's start the problems. In this particular question, you have to find the phase sequence of the set of the voltages. The given voltage is VAN, that is phase voltage 200 times cosine of omega t plus of 10 degree, VBN and VCN. So voltages can be expressed in phasor forms, as you know that if you compare this with the standard equation, that is V is equals to maximum voltage cosine of omega t plus theta, or current is equals to maximum current cosine of omega t plus of phi. So in phasor form you need to write the magnitude and phase angle only. So just express these voltages into their phasor forms. You will get the first voltage, that is 210 degree, and it is given in the question. The voltage can be expressed in phasor form, and the phase sequence is ABC. So you just need to because the first phase is 120 degree apart from the second phase, and the third phase is 240 degree apart from the first phase. So if you add up 120 degree in the second phase, that is minus 230, you will get in this problem, assuming positive phase sequence, so VBN is given to you. You need to find VAN, VCN. So what is VAN? Actually, the first voltage leads the second one by 120 degree. So if you add up 30 degree to 120, you got 150 degree, right? So first voltage is 120 degree, it leads the second voltage by 120. So when you add 120, you get 150. And the third voltage, that is VCN, it is behind the first voltage 240, and you may You may minus it by 120, that is the second voltage. If you, it is behind the third one, 120. So if you from 30 degree, if you minus 120 degree, you got minus 90 degree. So you will get the positive sequence voltages. All positive sequence voltages are there. Very simple. Let's move to this summary, and this summary shows to you the all connections of YY system, and these are the phase voltages and phase currents, and these being these phase voltages, and these being line voltages and line currents. So see, start from YY. Your phase voltage, that first phase voltage is termed as reference voltage, so it's the angle being 0 degree. The second one being 120 degree apart from first one, so minus 120 degree. The third one being my 240 apart from first, but if we see the third one is plus 120 and minus 240 being same, right? Here we can write minus 240 as well. So same thing. Similarly, because this is Y connection, we know that in Y connection, the line voltage, that AB is line voltage, it is under root 3 times of phase voltage. And if you consider this phase angle, that is 30 degree, you can from a previous lecture, phasor concepts, if you go to slide 17, slide 14, you find that the line voltages are 30 degree behind the phase voltage. So that was 30 degree appears in the phase voltage of YY connection. So the line voltage being 30 degree behind the phase voltage. It was under root 3 times YY connection, we know. Similarly, the other phases, the second VBC minus 120 degree apart from first phase, and the third one is 120 degree apart from second phase. And what is the currents? Line currents are simple. The line voltage, that the phase voltage over phase impedance connected in Y. And what is the line B current? Line B current is again uh, because the currents are being same, but the phase angle of minus 120. The second phase current is 120 apart from first line current, sorry, and the third line current is 120 apart from the second line current. So these are the values for the line currents. These are the values of the line voltages when the source and the load are connected in the pattern that is Y-Y. Both are star connection. Now come towards delta-delta connection. In delta-delta connection, the phasor voltages in delta, we have the property that is line voltages and phase voltages being same. So in delta-delta connection, yes, the phase voltage, the first phase is reference, so 0 degree. The second phase minus 120 degree, and the third phase with respect to second phase is 120. Either you write here minus 240 or 120, same thing. So the line voltages and the line currents in delta delta are being same as phase currents. That's why here written same phase voltages. Okay. So what is the value of phase voltage in delta delta? The phase voltage is nothing but the phase voltage over phase impedance connected in delta. Respective phase, that is AB, you need to VAB and V delta. Respective VBC voltage over Z delta, that is impedance. Current is nothing but voltage over impedance. Similarly, the case of ICA. And when you see the line currents in delta connection, the line currents being equals to root 3 times of the phase current. And if you consider the phasor, you see that respective line current lags the phase current by minus 30. That's why minus 30. In this case, it was 30 degree. It was leading. It is lagging. So minus 30 degree. The second one is minus 120 apart from the first, and the third one is minus 240 or plus 120. Same thing. So these are the values of the line currents in case of delta delta. In case of Y delta, you see, in the case of Y delta, you have you have the all the same properties of Y on this side and same properties of delta on this side as we discussed. And when you have a connection that is delta and Y, we have all the properties that is delta on this side and Y on this side. Hopefully you understand. You just not need to memorize the table. You need to just recall the values. Actually, you must know the phase current and line current relationships, and you must know the lagging and leading effects of these phase currents. So just refer to the phasor diagram. You will go quickly go through from that, and you will memorize it. And you will, when you practice it, it will comes in your mind automatically. No problem. By considering these properties, we are going to solve the numerical problems, that is, in which our source may be connected to Y and load may be connected to Y. Then our source may be connected to Y and the load may be connected to delta. And maybe our source is connected to delta and load is also connected to delta. And finally, our source is connected to delta, and the source is connected to delta, and load is connected in Y pattern. So let's move on. Let's consider this example. Calculate the line currents in three-phase wire YY system. In this figure, it is clear that the voltages are given to you, the phase voltages, and the line impedance. This one is the line impedance, and this one is the load impedance. So you need to calculate the line currents in three-wire YY. This is three-wire YY system. See, the source is YY, that is, all three sources are connected to a common point, common node. That's why it is Y. All three loads are also Y. See this point. All three loads are connected in Y pattern. So each load, that is phase A load, connected with wire A, phase B load is connected with wire B, phase C is connected with wire C, and each line have the impedance that is 5 minus J21, and each load has an impedance that is 10 plus J 80 ohms. You must know what is minus J, what is plus J. Minus J means the load is of the nature of resistance and capacitance, and plus J means the load is in the nature of resistance and inductance, because inductive reactance is positive J and capacitive reactance is minus J. So let's start the solution of this problem. Three phase circuit balance, it may have replaced it with the single phase equivalent circuit because it's balanced, so just we replace it by single phase. You can say we obtain IA from a single phase analysis. What is current IA? It is nothing but the phase voltage divided by phase impedance. In this case, the impedance is nothing but the sum of these two impedance, because 5 minus J2 is connected series with the 10 plus J 80 ohms, 8 ohms, sorry. So when you add up these two impedance, you will get the total impedance which is connected in ZY pattern. That is, this is line impedance and this is load impedance. So when you combine both these impedance, you will get one impedance. And what is the current? Current is nothing but voltage. It is a ratio of voltage over impedance. So when you divide that phase voltage by phase impedance, you will get the phase current actually. So total impedance is 15 plus J6, and when you can convert it into phasor, you will get 16.15 angle 21.8 degrees. So finally, you will calculate your current by putting your phase voltage, that is 110 0 degree divided by impedance. You will get the current. Since the source voltages are in positive sequence, because see, the first one is A, the second one is B, then third one is C. So this is positive sequence A, B, C. Since these are in positive, so the line currents are also in positive sequence, because the voltages are in sequence of positive, then line currents also in positive sequence, that is IA, then IB, then IC, and of same magnitude, just the difference of phase angle. So the line current, that is IA, is 6.8 minus 21. So what is this first? This was a line current of phase. So similarly, when you calculate your line current IB, you have to nothing to do, but just the second current is 120 degree apart from the first current. So when minus 120 minus 21.8 minus 120, you will got minus 141.18, right? The second line current, because second current line current is 120 degree apart from first line current. So you just need to minus 120 from this angle, you will get this angle minus 141. And finally, the third current, that is IC, the third current is minus 240 apart from the first current. So when you minus 240 degrees from the first current, that is minus 21.8, you will get minus 26 1.8 degree, or you may write this one as a 98.2 degree. Why? Because if you minus this angle from 360, you will get 360 minus 261.8, you will get 98.2. Either way you can write like this or like this, both are okay. So I think this problem was very easy, and you understand very well. Let's move to the next problem. So the phase current, the phase current is nothing but the line voltage over the phase impedance. Because this is a star connection, the line voltage and phase voltages being same, so we use same line voltage as a phase voltage in this case. So phase current is nothing but phase voltage over phase impedance, and phase voltage is 173.240, and the phase impedance is 8 point, as we calculated earlier, same. We got the phase current 19.36 angle 13.43. So similarly, we get other phase currents, that is IBC and ICA, and we know from the property of three phase, IBC, that is the second phase current, is minus 120 apart from the first phase current, that is IAB, and the third phase current is minus 240 or plus 120, same thing. So just you put the values and you will get these values, right? So see, because it is a balanced Y-connected system, the magnitude of the current being same, that is 19.36 in all the cases, but the angles are different. See, the angles are different. So these are the phase currents values. So what are the line currents? Because it is delta connected, so we know that the line currents are under root 3 times of phase currents, but minus 30 degree. Recall from the table that respective line currents leads to respective phase current by minus 30. So the magnitude being same, just multiply by under root 3, you will get the line current in delta connection. We know in delta connection, the line current being larger. So keep that property in your mind. The line current being larger, so it comes after multiplied by under root 3, it comes 33.53 minus 16.57, and respectively you will calculate the other line current, that is IB and IC, just by putting these values, that is minus 120, minus 240 or plus 120. So you will get the other. See, in this case also, all the values of line current being same with different phase angles, because it is balanced system. So the magnitude of currents and voltages being same. In this case, we need to find the calculate the phase and line currents. See, calculate the phase and line currents. So we calculate all line and phase currents when our system is the source is connected Y connected, and is the source Y connected is connected with the delta connected load. This was a case of Y delta. So consider another example. In this example, we have a balanced delta connected load having an impedance, a balanced delta connected load impedance of this value is connected to a delta connected. This one is delta delta, and positive sequence generator having VAB, that is VAB means the line voltage 330 0 degree. Calculate the phase current of the load and the line currents. This one is delta delta case, in which you have to calculate the phase current and the line currents. So let's just start the solution. The load impedance per phase is nothing but is given to you, but you need to convert it into the phasor form. You will get this value. So what is the phase currents? Phase currents are nothing but phase voltage over phase impedance. So in this case, straight away phase voltage is given to us, and because it's delta connected, so the line voltage and phase voltage being same, so you use the line voltage is given to you, but you use that same line voltage as a phase voltage because of the property of delta and balance characteristic, right? So same voltage, that is 330 degree, 330 0 degree. The voltage that was line voltage you can use as a phase voltage because in delta delta, and you just divided it by impedance, you will get the respective phase current, that is IAB. Similarly, you get the respective phase currents of IBC and ICA just by minus 120 degree from the first phase and minus 240 or plus 120 degree from the second phase. So these well see in all the cases the magnitude of the current being same because it is a balanced delta connected system, but the angle being different. The phase angles are the first phase angle 36.87, second minus 83, and the third one is 156.87. The phase angles are different. Let's move for the other part. For a delta connected load, the line current always lags the corresponding phase current by 30 degree. Recall from the phasors. So our line current in delta connected, the line current always lags it lags. That's why minus 30 degree. So you will calculate the line current just by multiplied by the you will get the phase current by multiplied by under root 3 times minus 30 degree lagging effect. So you calculate in this way, you will got 22.86, and respectively you will calculate the other line currents such as IB, such as IC, just by second line current. The first line current, the angle should be minus from the first, that is 6.87 minus 120 degree, you get minus 113.13, and minus 113.13 when you plus 120 degree to 36.87, so you get 126.87. See, the same practice is going on, same practice. 120 add to 0 degree, 120 degree add this to 36.87 degree, you will get 156.87. So the same practice. Hope you understand. Now consider this example. In this example, you see the balanced Y connected, the balance Y connected load with a phase resistance of 40 ohms and reactance of 25 ohms supplied a balanced positive sequence delta connected source. So this one is Y delta with a line voltage of 210 volts. Calculate the phase current, use VAB as its reference. So let's just start the solution. The load impedance is just you have to add up the resistive and reactive part, that is 40 plus j25, and convert into phasor form. You will get 47.1732 degrees, and it is given to you that line voltage, that is VAB, line voltage 210 0 degree. So when delta connected source is transformed to Y connected source, so when you transform this, we must know the property of delta connected, that is Y connected, that is line voltage equal to under root 3 times of phase voltage. So you will get the phase voltage by just divided by line voltage by under root 3 times, you will get the phase voltage. So by minus 30, because of the property, it lags the respective voltage by minus 130, minus 30 degree, you will get this value. So the line currents are nothing but the line voltage over line impedance, but there is no concept of line impedance because you have to divide the phase voltage divided by phase impedance. So the phase voltage comes out to be this one, that is we calculate already, and the phase impedance already mentioned in the problem. So the line current being this magnitude. Now use the same property that the second line current is minus 120 apart from the first, that is minus 120 minus 62, you will get minus 182, and the third line current is 120 apart from the first line current. So when you add up 120 to minus 30, you will get 58 degrees. Sorry, students, I missed that point. This 58 degree comes from when you minus 62 degree plus 120 degree, because the third line current is 120 apart from the first. So when you add up 120 to this minus 62 degree, you will get 58 degrees. So hopefully you understand this problem. Let's move to another problem. Before moving to the problem of the power, we must know the values of the power. One is active power, that is true power, or active power. It's the units of active power is kilowatts, that is kW. It is nothing but VPIP, that is phase power, phase voltage multiplied by phase current, and cosine of the phase angle between voltage and current. You will get active power, that is kilowatts. One is reactive power, that is phase voltage multiplied by phase current multiplied by sine of that angle. Remember, when you multiply by cosine, you will get active part of the power. When you multiplied it with the sine angle, you will get the reactive power. That is kilovolts ampere reactive. The unit of reactive power are kVAR, and the units of active power are kilowatt. And this is apparent power, that is total power generated from the source, and the unit of apparent power is kilovolt amperes. It may be expressed in uh, complex form, that is real power plus of imaginary power, that is reactive power. So P plus of JQ, or VP IP conjugate, the current conjugate. So it may be represented into the complex form, the apparent power. Remember, these formulas will be used in the upcoming problems. Thank you.